All right, welcome back. Let's get into the next unit, which is energy. The first thing before we get going, though, is that this unit heavily relies on forces, which a lot of the units have already. But this unit is going to use net force a lot, and so make sure you review how to find net force, how to draw free body diagrams. That'll all be important in this unit. If you don't remember how to do that, I put a worksheet on the Canvas page. It's an optional worksheet. It's not going to be graded. There's no submission for it, but it would be good. It would be good to go ahead and do it. It's not very difficult. I don't think you should be able to do it with some review of some reviewing of your notes within 10 minutes maybe. And so that's what we're doing in class to start off with. So energy, its literal definition. So if you Google the physics definition, it's going to say it's the capacity for doing work. But what does that mean? Work is actually a physics definition. It's actually what we're really going to be talking about today. We're not going to dive super deep into other energy. And so, but ultimately, when we think about energy, you should just think that if you have energy, you have the ability to do something. If something has energy, it has the ability to do something, to do things. Don't overcomplicate it. It's a scalar. There's no direction to energy, so it's just an amount. You have this much energy, or you don't, or you have this much energy. It's a scale. There's no direction to energy, like we did with vectors, or velocity. Remember that velocity has a number, but it also needs a direction. If I am traveling on the highway, I have a direction to my motion. That's my velocity. But energy is just a number. You can gain or lose energy, but then that's still not a direction. You need some sort of physical direction. That's just in or out. The unit is joules. You probably have heard this before. We talked about a bunch of different units for energy, for thermodynamics, but the only real one we used was joules, and that's going to continue. The only real unit for energy we're going to use is joules. All right. So, work. As we move on in physics, I'm hoping that this has become more familiar, but I haven't really ingrained this in you. In physics, we have things called definitions, and definitions are not always verbal definitions. Like where I gave energy, I gave you some words here. That is my definition, quote unquote. In physics, normally when we get definitions, they're an equation. This is what work is defined as. Work is defined as force times displacement times cosine theta. That's its definition. There's other things you can think about work. There's other things we can do to think about work and get an idea of what work is, and conceptually and feel it. But anytime you really are worried, okay, what are they talking about work? Go back to this definition. Use the equation. This is my definition. This is what work is. Work is just an equation. It's just force times the displacement times cosine theta. Okay. So what do all these mean? Well, force. What is work? It's if we have the work done by a particular force, we might have the force, in this direction, but maybe the motion of the object is actually in this direction. Okay. Actually, let's start with a different example. Let's start with a more simple example. Let's just say we have a box on a surface pushing to the right. Okay. Box is pushed to the right 5 meters with 40 newtons of force. What is the work done by the push force? So we have a box on a surface. We're pushing to the right with a force of 40 newtons. And then, of course, if we push to the right, we're probably also going to move to the right 5 meters. And let's say we move 5 meters. Okay. The work is defined as the force times the displacement times cosine theta. And so all we have to do is plug in the numbers. The work done by this force, by this push force, is 40 times 5 times cosine theta. But what is theta? Theta is the angle between the two vectors. And so what you do is you lay these two vectors, this force vector and this displacement vector, over each other. So let's say we have that there, and then this here for 5, 40. And tell me the angle between them. Well, they're going in the same direction. So there is no angle between them, right? Therefore, it's an angle of 0. And so we do 40 times 5 times cosine of 0. For those in pre-cal, maybe you can do this in your head, but if you don't know, you can still do it in your calculator. Just make sure you're in degrees, not radians. But it turns out cosine of 0 is just 1. And so this is equivalent to 40 times 5 times 1, which is just 40 times 5, which is, what is that? I'm thinking 200. But it's been a while, so I'm rusty on my math. 200 joules. That's the work done by the push force on the box. Okay? Let's ask ourselves another question. This box, if we were to draw a free body diagram of that box, we have a push force of 40 newtons to the right, but we also have a gravitational force down and a normal force up. Okay? And so we can ask ourselves, what's the work done by the normal force? Well, the work done by the normal force is the normal force times the displacement times cosine theta. So whatever the force is times the displacement times cosine theta. In this case, we actually don't know the normal force, right? I never gave you that information. So maybe it's something you have to solve for. Remember that if I gave you the mass here, you would know that the forces are balanced. And so in this case, Fn is equal to Fg, which is equal to mg. And so you could calculate the normal force, but I actually didn't give you the mass. Let's see if we can solve it anyways. Delta x is 5. And cosine, well, what is the angle between the two forces? If the displacement is to the right and the force is up, that means the angle between them is 90 degrees. So let's multiply by cosine of 90. Go ahead and punch in your calculator cosine 90 degrees and get an answer. If you do this, you should get the answer that cosine 90 is equal to 0. Which means it doesn't even matter what the normal force is. If this is 0, the whole thing is 0. So the work done by the normal force is 0. And that's a key idea. If the force and the displacement are perpendicular, you may want to write this down. If the force and the displacement are perpendicular, that means that the work done is 0. And think about it. What energy is the normal force providing to that object? The normal force isn't doing anything, right? It's not helping the object gain any energy or anything because it's just sitting on a table. It's being pushed to the right, so that force to the right is adding some energy to it. But the force upwards, the normal force, isn't really doing anything. It's not accomplishing anything. It's just there to balance the gravitational force. But besides that, it's not adding energy. And so the work done is 0. Okay. A box is pushed to the right 5 meters with 40 newtons of force made at a 30-degree angle to the horizontal. So let's say that we have a box on a surface, and let's say you're pushing on it downwards at an angle of 30 degrees. Okay. So if we draw a free body diagram, it looks like this. We have a normal force up, gravitation down, and then we have some sort of force at an angle of 30 degrees. Whenever we did free body diagrams initially, I would have told you that, hey, you need to split these components up. This time, we're not going to worry about splitting components up. We can leave our diagram as it is. We don't need a working diagram. If we want to find the work, all we need to do is do force times distance times cosine theta. So the force is 40 newtons. The distance is still 5. But what's the angle between them? Don't just assume it's 30. I think in this case it is 30. But don't just assume it's 30. Go ahead and draw your angles. Draw the force vector and the displacement. The displacement is to the right, right? We're going along a surface. But the force is being pushed down. The force is downwards at 30 degrees. What's the angle between them? Well, in this case, it is 30 degrees, right? That angle between them is 30. That won't always be the case. If we have some sort of slope or something, we might get some other answers here. So in this case, it's cosine of 30. So we can type that into your calculator, 40 times 5 times cosine 30, and you should get 173.2. And that's joules, and that's our answer. Okay. We also have some graphs we need to study. There's not much to this. We're not going to go deep into graphs like we did in kinematics. The main thing you need to know on force, you need to know force position graphs. Force position graphs. Okay. And all you need to know, the slope is not really meaningful for us, but you need to know the area underneath the curve on a force position graph is the work. Okay? So if you have a force position graph and I ask you for the work done on an object, you should be able to find it. So let's go ahead and find the work done in the first 5 meters of this object. Okay? If we want to do that from here to here, we just need to find the area of this triangle. Well, the base is 5. The height, it goes up to 25. And then we want to do 1/2 times that because it's a triangle. So 1/2 base times height. So we do all this 1/2 times 125, whatever that is. 125 divided by 2. You get 62.5. And that would be our work done because the work is the area underneath the curve. So let's get a more conceptual definition because I told you what the real definition is. The real definition of work is just the equation. I like to go ahead and put in here, this is not, if you take a higher level physics course in college, if you take a calculus-based physics course, you will get a different definition. You'll get the more proper definition, but we don't have calculus. This is not a calculus-based course. We do algebra in here, and so I'm giving you the algebra-based definition. The fancier one looks something along the lines of this, and it looks really weird. Don't worry about it. It's not anything crazy. It's actually pretty easy to use, but you need to know calculus to do it. I just like to throw that in there. So here's our definition for our class. Work is equal to FD cosine theta. Some important things here. All right, so work is measured in joules, right? We established that with the examples, therefore must relate to energy. And so really when you think about work, you need to think that work is the change in energy in a system. Okay, it's a force acting over a distance. It's affecting the energy in that object somehow. It's not always adding energy necessarily. The energy may be, but it is changing it, okay? Yeah, so it's really just a change of energy. So I'm not going to get too deep into this because we haven't talked about different forms of energy, but I think a lot of us know the difference between gravitational energy, right? Gravitational potential energy and kinetic energy. So some of you guys might know that gravitational potential energy, we write it like this in this course, U of G. We'll talk about it next class, so you don't need to write it down if you don't want to. So this is the energy at a height. If you go, the higher you go, the more potential energy you have because the more work gravity can do on you. And then you probably have an idea of what kinetic energy is. Kinetic energy is just energy in motion. It's the kinetic of a moving, or the energy of a moving object. If you think about a ball falling off a cliff, it starts with a bunch of potential energy, but at the bottom has kinetic energy. The energy over time actually doesn't change. The total energy is not changing in the object. The object is not creating energy, and nothing's really acting on the object in order to give it energy. What's really happening is the energy stored in the object as potential energy is being converted into kinetic energy. That being said, work is still being done because there's a change in energy. Well, what is the force doing the work? Well, think about it. What force is causing the object to fall? It's gravity. So the force of gravity is what's doing the work on the object. And so when we think about work, don't always think about it's adding energy necessarily or losing energy, but energy is changing in the object. Okay? So let's do another example. I think this is the one I wanted to do for to get some other angles in here. A wagon is 50 kilograms, is pulled at an angle of 35 degrees with a force of 100 newtons on a frictionless surface. The wagon travels 15 meters. Find the work done by each force and the network. Oh yeah, never mind. This is just so we can find network. So let's do a free body diagram. We have a wagon problem. Remember that we did force of gravity down, we had normal force up, and then we had some force at an angle of 35 degrees. And this is 100 newtons. We can call it the applied force, F1. Okay. If we want to find the work done by each force, let's do them all separately. So let's do the work done by the normal force. Before we can do that, we need to figure out what the normal force is. And the previous, well, actually, remember, we don't need to. My bad. I just thought about this. We don't need to, right? This is what makes this easier. Normal force times the displacement is equal to cosine theta. And wait, we just discussed this, right? We don't need to find the normal force because let's look at the where this wagon is going. It's to the right. It's traveling 15 meters. And the force is straight up. And so we know they're perpendicular to each other. Therefore, we discussed that the normal force does zero work. And this is mostly the case. The normal force is going to usually do no work. It's not always the case, especially in an elevator problem. Okay, but if its object is moving across the surface, then the normal force is going to be zero, right? Because if it's moving across the surface is perpendicular to the normal force. But if the surface is doing the pushing, like in an elevator, then we'll have some work done. All right, let's do the work done by gravity. But similarly, gravity is straight down, and the displacement is still straight across. So funnily enough, gravity also does no work, which again should make some sense because the force of gravity really isn't adding energy to the object at all or taking away energy. It's not really, it's going to, in some effect, affect the object because if there's maybe friction on the surface, gravity is going to make more friction occur, which might be taking some energy away from the object. But directly, gravity does nothing. Gravity is just acting on it, but the object's not falling, and so it's not really adding any energy. The only force we really have to worry about is the applied force. So what is the work done by the applied force? Well, the applied force was 100. The displacement was 15. And the angle between them was 35. But let's double check that. Don't ever just guess. Draw your displacement. Displacement's to the right. And my angle of the force is at a 35-degree angle above the horizontal. Okay, that looks like it's 35 degrees between the two, right? So therefore, it is cosine 35. So then we can type it in, 100 times 15 times cosine 35. And we get a big number here. That's fine. We have bigger numbers than the last time, so we're going to get a bigger number. That's the work done. All right. And then now I want to find the network. Remember this number right here. Okay. There's two ways to find the network. Okay. The first way is if we've already done what we've done here, you just add up all the work. Therefore, it's 128.7 joules, right? 0 plus 0 plus that number, that's it. Network means sum, right? So if we just add up all the work added to the object, then that gives us the network. And so that's one way you can find the network. If I ever ask for this, which I will ask in a question. So if you want to ever find the network, find all works, then add, then sum. The second way is to find the net force. Then calculate with work equals FG cosine theta. Okay. So let's go back and see if we remember how to find net force. Net force, we actually need to go ahead and we do this free body diagram like normal. FG and then F1. And then we went ahead and did a working diagram. If you remember, when we found out force, we did the working diagram. We realized that F1 has a component upwards, F1 sine theta, and also has a component to the right, F1 cosine theta, and also has FG down. Okay? And then we would remember that when we find the net force, we're looking for, okay, was the sum of all the forces in each direction. And so we did the T chart, but we can kind of skip a step here because we know the Y side, this wagon is not flying and it's not falling through the earth. I won't give you flying wagon problems in here at least. Therefore, the sum of the forces in the Y direction are 0. And so we only have to worry about the forces in the X direction. Therefore, the net force is just, well, there's only one force in the X direction. It's F1 cosine theta. So if you want to type in F1 cosine theta real quick to your calculator, we have 100 cosine 35. 100 cosine 35 is 81.91. And that's our net force. And if we want to find the work done, what we do is we do work equals FD cosine theta. What's the force times the displacement times the cosine theta? Well, the force is 81. The net force is 81.91. The displacement is 15. But what is the angle? Some of you might say, oh yeah, it's 35, right? Hold on. The net force, F1 is at an angle, right? The applied force is at an angle, but the applied force was 100. Our force here is 81.91, so it's obviously not the same force. We're looking for the net force. What direction is the net force in? Well, these forces go straight up and down, and this force right here is our net force. Our net force, we decided, was F1 cosine theta, and it's going straight to the right. Our net force is straight to the right. And so is our displacement. Therefore, the angle between them is 0. And so now we can go ahead and multiply by 15 and times by cosine of 0. And you should get that same answer we had before. And some of you may have picked up, I mean, we essentially did the same thing. We did F1 cosine theta times the displacement essentially overall, because we took our net force, which is F1 cosine theta, and multiplied by the displacement, and then cosine theta, which is cosine 0, which is 1. So, and yeah, that's how physics works. So, if this way is more, I think this way can be more confusing for you, and so I suggest just doing the original way. Find the work done by each individual force, then add them all up to find the work. But if you like this way, to me, this is actually shorter to do in my head than to find all the individual works and then to add them up and to find an answer. If I can just find the net work real quick, then I can do it. But I think this way requires more understanding of the physics. And so this might take, a couple of days, maybe a week or so to really understand how to find it this way. And so for now, use the first method. Find all the individual work done and then add them all up. And that also gives you the net work. Next time we will do energy types. I think I have them in here, but we'll study different energy types. Mainly, there's only 3. There's potential energy, there's kinetic energy, and there's one we may not have discussed before, but it's spring potential energy. If we have springs, then they also have some sort of potential energy to them. But we'll do it next time. So I'll let you get started on the homework. Have a good day.